This app lets you play with very important task in statistics. It's a comparing means of two groups, meaning you have two samples randomly taken from two different populations, and you would like to find out how likely these samples came from populations with equal means. Okay. So let me show you how it works here. So first of all, this big plot is our populations and samples. So this is all the data that we have. You can see that, in fact, what we are dealing with, it's outcomes of a process which we run at two different temperatures, 120 degrees and then 160 degrees. And then what we measure as outcome, it's a yield. It's a yield of final product. For example, we are talking about a chemical process, and then it's a yield of final product in milligrams. What you see as distribution curves here, it's all possible yields. So this blue distribution curve shows you all possible yields you can get if you run a process at 120 degrees. Of course, even if you run the same process at the same conditions again and again and again, the final yield will be a little bit different because you always have influence of different random factors, right? So therefore, you will have some variation here. In our case, the outcome is described by normal distribution, which has average around 100 milligrams, and then we have a certain spread, which we will call a noise in this case. And then this is the second population. These are all possible outcomes of a process if you run it at 160 degrees. And you can see that by default at the beginning, it also has an average outcome equal to 100 milligrams. So it means that temperature actually doesn't have an effect on the yield. So it means that it doesn't matter at which temperature you run the process, the average outcome will always be the same, and it's 100 milligrams. This is the expected outcome. Of course, when we run the process, we do not have exactly 100 milligrams. We always have a different value somewhere from this distribution and somewhere from this distribution, right? And the problem is that if you run this process limited amount of times, in my case, you can see I ran this process at 120 degrees 3 times, so I have 3 different outcomes. This is my sample 1. And then I ran this process also 3 times at 160 degrees. This is my sample here, so you can see also 3 different outcomes. And then if I compute the average of my sample 1, this one, and then sample of my average of my sample 2, this one, you can see that these average values are not the same. Although the population average values are the same, we can see that we have an effect from the temperature, right? So you can see that actually the observed effect is minus 15.25. And in this case, it's minus because I have average of the first sample minus average of the second sample. Okay. Strictly speaking, that it means that when we ran our process 3 times at 160 degrees, in average, we got by 15 milligrams more of the final product. However, in this case, we know that actually there is no difference for the populations, right? And the idea is that can we see that this effect that we observe is actually a random effect? This effect is observed by chance. Yes, we can. And we have 2 possibilities in this case. First of all, we can measure the uncertainty of this effect. In this case, we compute a standard error for the difference of means. And then we take a certain standard error to the right and then a certain standard error to the left. And this certain, it depends on, first of all, on degrees of freedom, on how big your sample is, but also it depends on the confidence level. So in this case, I use 95% confidence level. So I use t-distribution, and then I just compute t-score and took this t times standard error to the right and then t times standard error to the left. And this is the confidence interval. And what confidence interval tells us? It tells us that the observed effect is minus 15. This is what we see here. But in fact, this effect can be somewhere between this one and between this one. And then you can see that it can be negative, but it also can be positive. So it means that statistically, we don't have an evidence that running process at 120 degrees is indeed lead to a smaller average compared to running process at 160 degrees, because it can be indeed like this, but it can be also vice versa, right? So it can be other way around because the effect can be also positive. So this is the confidence interval. It tells us where the real expected effect is, and then you can see it can be anywhere from anywhere between these 2 points with 95% confidence, right? So we still can also have a possibility to have it even beyond this interval. Okay. The second thing you can do is to make a test, and this is a t-test, so-called t-test. So in this case, what we do, we do the following. We take a ratio between the observed effect and the standard error, and that's what we call a signal-to-noise ratio in statistics, or in this case, because I use t-distribution, it's a t-score. So you can see that this observed effect is approximately 2 times larger than the standard error. So the t-score will be approximately 2. And then I compute a chance to get an effect as big as this one or even bigger, assuming, this is my null hypothesis, you see, assuming that the real effect is 0. And this is, I know that my null hypothesis is correct in this case, right? And you can see that the chances, it's a p-value. It's 12.2%, 0.122. That means that if my null hypothesis is true, I have 12% chance to get a sample as extreme as mine. So it means that the effect, observed effect, is not 0. It's, in this case, it's a negative effect, or even larger if the null hypothesis is true. So this is the chance. And it's 12%. So in this case, I cannot reject my null hypothesis. So I accept it. Okay. And then this shows you how many times actually I rejected null hypothesis. In this case, I work again at 95% confidence level. It means I compare the p-value with 5%. And you remember that in this case, we have 5% chance to make a wrong decision. So we will reject null hypothesis, although the null hypothesis is correct, right? And this is what we can change. We can change the effect. So right now the effect is 0. This is expected effect. It's a theoretical effect, right? We will play with this in a minute. And then we can change noise. It's a spread of these values for the populations. And then we can change also the sample size. So let me start just taking a lot of samples of sample size 3 and see how often actually I will reject null hypothesis. Although I know that null hypothesis in this case is correct, right? So you can see I took some already. And then let me just stay here, stop here. You can see that I ran this process 68 times. At each time I ran it at 3 times at 160 degrees. I ran it 3 times at 120 degrees, and then I compute mean, and then I do this inference, right? And then you can see that 4 out of 68, I incorrectly rejected null hypothesis. So it means that in 4 out of the 68 runs, I made a decision that I have an effect, I have a significant or reproducible effect, but this decision was wrong because we know that there is no effect at all, okay? So in this case, you can see that the number, the percent of wrongly rejected null hypothesis was approximately 6. But if I keep going, it will be 5% because this is exactly what the confidence level means, right? So 95% confidence level, it means that we have 5% chance to reject correct null hypothesis, right? And that's how you actually should think about this threshold, right? If the p-value is smaller than the threshold, it doesn't mean that you have an effect. It means only that the chance that it actually came from the population where there is no effect is not very big, right? But you still have a chance, 5% chance to make a wrong decision. So 5% chance that you will claim that you see an effect, but in fact, in reality, there is no effect. If you think about population, the expected effect is 0, right? And then this 5%, it doesn't depend on anything. I mean, if you change the noise, for example, if you make it bigger, let me make it smaller, right? So noise is smaller. When the noise is smaller, it means also that the standard error is smaller. And the ratio is more or less the same. And then you can see we still have 5%, approximately 5% cases where we actually reject null hypothesis, although the null hypothesis is correct. I can go even further and, for example, increase the sample size. So now I ran it 30 times here and 30 times here. And then you can see if I repeat this many, many times, I still will get approximately 5% incorrectly rejected cases. So I will reject null hypothesis incorrectly. Okay. In my case, it's 2.2% because I will reach 5% only when this number is really, really big. Okay. So select this threshold smartly and remember that if p-value is smaller than this threshold, it doesn't mean that you definitely have an effect. So if you want to avoid claiming that you see an effect, although there is no effect, just reduce the significance level down to 1% or even smaller. Now, what happens if you indeed have an effect, right? So let me get back to sample size 3, and then the noise will be, for example, 10 again. And then I will make an effect. For example, I will make an effect of 10. The difference between the population means is 10. It's one standard deviation if we talk about one single population. So in this case, the null hypothesis is wrong. It means that we have an effect, right? Let's see how often we will be able to see it, because right now in this particular case, you can see that I cannot reject my null hypothesis. Although it's wrong, but I cannot reject it because the p-value is 0.07. I work with 5% confidence level. So I cannot reject my null hypothesis. In this case, I cannot I do not have enough evidence that my null hypothesis is incorrect. There are many things that influence this type of error. First of all, it's how big the effect is. The bigger effect, the less chance that you will not be able to observe. How big the noise is. In this case, noise will influence this percent of the errors, and also how big the sample size is. Okay, so let me show you an example. So I will start again from this small sample and relatively large noise. So let me make a lot of tests and see how often I reject a null hypothesis, right? Then you can see that I reject null hypothesis, like you can see only 20% of time. This is my power of my test. Only 24% in this case, but I think it's about 20. I have a chance to claim that I have an effect, that I have evidence, statistical evidence for this effect. And this chance is only 20%, because in 80% of the cases, my p-value will be too large to reject the null hypothesis, right? And this is a very small chance, right? So it means that I have very little chance to observe an effect of 10 milligrams, although the effect is present in this case. How to increase this chance? How to increase, it's called a power of test. Well, there are actually several possibilities. And first of all, of course, it's reducing noise. So if I reduce noise, for example, down to 5, and then if I start doing this again, you can see that the number of rejection is much higher, right? So if in this case, it's approximately 60%. So it means that I have a power of 60%. In this case, I have a 60% chance to to get this statistical evidence that my effect is indeed present. Okay. And the second possibility is, of course, to increase the sample size. The larger sample size is, the larger power we have. So in this case, I believe that I will have almost 100. Yeah, indeed, I have 100% power. So in all cases so far, I reject my null hypothesis. So I can clearly see an effect. So what it means? It means that if you know that your effect is small and you want to observe it, you want to have a statistical evidence for a small effect, you need to increase the sample size, because usually you cannot change noise. It's very difficult. You can, of course, do a better sampling, for example, to reduce noise. But the easiest thing to do is just to increase the sample size. Okay. And then you can see also the other effect of the larger sample size and smaller noise. It's much smaller confidence interval, because you simply, by increasing a sample size and decreasing noise, you decrease uncertainty in estimation of your real effect, right? So now your estimation of your real effect is quite narrow, is quite precise. Okay. So this is how it works.